Hello, hope you're enjoying your long weekend. So we're going to finish up our notes from Thursday talking about strong acids and strong bases. So strong acids and strong bases form what we call strong electrolytes, and electrolytes is just a fancy term for anything that creates ions in a solution. So because, as we mentioned before, strong acids completely dissociate, they form electrolytes because they're dissociating into ions. And again, as we mentioned before, the 7 strong acids, you just need to know these. Those are listed there, the same ones I gave you on Thursday. And again, all of those 7 strong acids completely ionize. Any that aren't one of those 7s, they do not completely ionize, and we'll talk about those next week with our weak acids. So for example, nitric acid, because nitric acid is one of the 7 strong acids, it will completely dissociate into hydrogen ion and nitrate. And so if we have a concentration of nitric acid of 0.2 molar, that is also the concentration of the hydrogen ion and the nitrate ion, but we're not worried about the nitrate ion. So knowing that that is also the concentration of the hydrogen ion, we can take the negative log of 0.2 and come up with a pH of 0.699. Now, if we had sulfuric acid instead, sulfuric acid, when it completely dissociates, it's going to separate into 2 hydrogen ions and sulfate ion. So in that case, the hydrogen ion concentration is actually doubled. So if we had 0.2 molar sulfuric acid, the hydrogen ion concentration would be 0.4 molar because of the 2 hydrogen ions. And so plugging that into the negative log, that would give us a pH of the sulfuric acid of 0.398. So we could go the other way, and if we have the pH of an acid, in this case nitric acid, we can determine its concentration by using 10 raised to the negative pH, so 10 raised to the negative 2.4. Remember, 2.34. Remember, we do have to include the negative on our calculator or it will give us a wrong value, and that gives us 4.57 times 10 to the negative 3rd, so that would be our hydrogen ion concentration. Now for strong bases, exact same thing is true. We're just dealing with bases instead of acids, but they too form electrolytes because they also completely ionize in water to form a metal cation and hydroxide ion. As I said Thursday in class, strong bases are all the alkali metal hydroxides, potassium hydroxide, sodium hydroxide, those are the main ones, but any of the alkali metals, and then the heavier alkaline earth metals, calcium, strontium, and barium, and usually we'll throw in magnesium, because again, as I said Thursday, magnesium's kind of on the borderline. So we calculate concentrations same way we do with pH for acids. It's just here when we're dealing with a base and we have pH, we've got to do that extra step. So we have the pH of potassium hydroxide of 11.89. So if we're trying to figure out the concentration, here's the reaction. So it's 1 to 1, and again 100% dissociation. So again, since we're given pH and this is a base, the base is forming hydroxide ion, so we have to convert the pH to hydroxide ion. So taking 14 minus 11.89, that gives us a pOH of 2.11, and then we can plug that into our 10 raised to the negative pOH, and that will give us a hydroxide ion concentration of 0.00776. Now we could have done it a different way, we could have converted the pH to hydrogen ion concentration by taking 10 raised to the negative 11.89, gotten a hydrogen ion concentration, and then converted it to hydroxide ion concentration using the kW. So that's the other possibility. I think that's a little trickier than the way I showed you here, but either way will work. Then same thing for calcium hydroxide. Again, we're given a pH as we usually are, even though we're dealing with bases, this of 11.68. Now here's the equation for calcium hydroxide, but this pH is based on the 2 hydroxides, so we don't have to do anything like we did going from concentration to pH. This is already measuring this just right now in pH. So again, we do have to convert that to pOH, which 14 minus 11.68 gives us 2.32. And again, we don't have to double or have that because that is a measurement of what is right here. So that is 2.32. And then again, we just like we did on the previous one, take 10 raised to the negative 2.32 gives us a hydroxide ion concentration of 0.00479. Now, if it wanted to calculate the calcium hydroxide concentration, then we would take this concentration here, because this represents the hydroxide ion, and have to divide that by 2, because the hydroxide ion concentration is going to be doubled that of the calcium hydroxide. Okay, but here from this pH, that is based on this right here, including the 2. So that's the only thing that we would have to do differently than what we did up here with the potassium hydroxide, is if we were trying to figure out the concentration of the calcium hydroxide as a whole, since that's a 1-to-2 relationship, we would have to divide that by 2. Okay, so hope that makes sense. And we could do it the other way as well, like what I explained up here. We could convert this to hydrogen ion and then use the kW to convert to hydroxide ion. We'd still get the same answer. So I hope this makes sense, and remember to finish up your homework and upload it to Schoology before 3 o'clock, and I will see you next week. Have a good weekend. Bye.